Alright guys, so we're making a satellite today. Say it's a cylinder, and our satellite has a length, diameter, it has some density. Density is, say, 2,800 kilograms per meter cubed. It has, it's hollow, so it has a thickness, and it has a mass. Let's say we know the mass already, 7,500 kilograms. And oh yeah, we know the Young's modulus of the material. So let's say that's about 71 gigapascals. Okay, so we want to size the thickness of the cylinder, and the first thing we have to do is we have to size the spacecraft for stiffness. And say for this problem, we're going to assume that the spacecraft is constant mass throughout the height of it. And of course what we're going to do is we're going to get a color. We're going to put this is my rocket ship. We're going to put it on the rocket ship, and when the rocket ship goes up, there's going to be a whole bunch of vibrations, and we know that the vibrations are going to be in the lateral direction. They're going to be well, the minimum vibration that the minimum natural frequency that the satellite can be 30 hertz, and in the longitudinal direction it can be 9 hertz. And based on the assumption that it's constant mass all the way through, we can use the equation for constant mass beam. From just looking up in your textbook, you can tell that the natural frequency is going to be, let's say we do the axial direction first. Let's say that's going to be, we know from looking that up that that'll be this. And we also know, based on what we have from our satellite, we know the cross-sectional area, of course. Let's put that here. Of course, that's going to be just thin-walled approximation, and the other values we have. So just by rearranging this, doing a little bit of rearranging, we can get the minimum thickness, and that's going to be based on the frequency we just had. It's going to be yeah, sorry, that should be like that. Like so. And if we want to do it in the lateral direction, we have another equation. It's going to be 0.56, slightly different. And by substituting in for what we know is the moment of inertia or the moment of area for a circle, we can say that's going to be pi times the radius cubed times t. So we substitute that in, and what we get now, if we rearrange all of these terms, is we get this squared that's just taking out the 2. Alright, and this is for the minimum frequency, we get a minimum thickness. Alright, so let's see. Do we have all these? We have the mass, we have, let's say for the length, we know that our length is going to be 4.1 meters. We know that the diameter will be, say, 0.937 meters. Alright, And so we have all of these values, and we have all of these values. And if we simply do some substitution, we can come up with the minimum thickness that we need to get this vibrational requirement. And so if we do it in the axial direction, that's going to end up being 2.12 millimeters. Yeah, I'm not going to calculate all this out for you guys, but then in the other direction, it's going to be 5.82 millimeters. So of course, to meet both requirements, then what we need is, of course, we're going to be using this one. Okay, so now maybe we just want to know what is going to be the structural mass of our satellite, and of course that's just the structure. We already know what, or have an approximation of what the total mass is going to be. So in order to do that, it's quite simple. We know mass is rho times volume. Of course, this is a cylinder, so we have the cross-sectional area, and we know the thin-walled approximation area for the circle, right? And so if we can just, let's see, we have the density already here, we have the thickness, so we can put in times pi was diameter times the thickness was my thickness, so that's going to be 0.00582. Putting everything into the right units, which I'm sure you can do. And where's my length? Times 4.1. We calculate all that out. Structural mass is 197 kilograms. Our original mass, our total mass was 7,500 kilograms. That's pretty good. That's pretty small. All right. That's it for this one.